on 3 examples of asymptotic notations. In this video, I will do 9 examples. It will be a little long. It will be more than 30 minutes. I hope I can control less than 40 minutes. All right, so when we start, let us start with our first question. I make a very simple question first. All right, the first one, show that n plus 2 belongs to big theta of n. Big theta of n. First, let us recall what is the meaning of big theta of n, the asymptotic notation. We learned 5 asymptotic notation. So let us quickly go through these 5 asymptotic notation. The first one, a little o, right? Second one, big theta. Third one, little omega. Number 4, big O. The last one, the fifth one, big omega. So these are all we need to learn in this class. Although there are a few more other asymptotic notations, but they are rarely used. So we do not need to talk about those. All right, so here, this one, we look at the second one, big theta. So what's the meaning of big theta? By the definition, we need to find 2 positive constants. Put 2 positive constants, C1, C2. C1 and C2, positive. Here, I do not have a lot of space. C1, C2, positive. Both positive. Then we want to make sure the inequality, remember, lower bound, upper bound, right? Lower bound, upper bound approximation of the given function. All right? So n plus 2, the given function. Okay, n plus 2 greater or equal to, less than or equal to 2 functions, multiple of n. C1 and C2n. Upper bound C1n, lower bound C2n. If you switch, it is not a big problem. If you switch C1, C2, it's fine. Just 2 different positive constant. 1 lower bound, 1 upper bound. That's all we need. All right. If you can prove, there is another hidden requirement. This inequality is true for n greater or equal to certain integer, non-negative integer, could be 0, non-negative integer n0. If you can do that, then we prove it by the definition. All right. So that's the procedure. Now, because in your homework assignment, I will give you this type of questions. So usually, based on my experience, several students, so they didn't watch the videos. So when they see these questions, so they just basically by their, intuition, they do not use the definition, standard definition way. All right, so let's start to work. Our goal to estimate this function n plus 2 from upper side and from lower side, 2 sides. So let's take a look. Which side is easier? Usually we want to start from the easier side. All right. Lower side easier, because we just dropped 2, n plus 2 greater than n. n is a multiple of n, right? N is a special multiple of itself. So here you can see when n greater or equal to 0, this inequality holds. And in this situation, we just take C2 equals 1. 1 multiple of n. So we have the lower bound estimate. Yeah, pretty easy. The upper bound, slightly harder, but not too much harder. Yeah. So let's look at the upper side. Upper side, we want to use another constant multiple of n so that C1n greater or equal to n plus 2 when n greater or equal to some n0 number. Yeah. Let's take a look. Can we find that C1? Right? Yeah. Look at this. Yeah. Because we want to use the multiple of n to control from the upper side, control n plus 2 from the upper side, or to cover, to make sure its value is greater than n plus 2 from the upper side. Yeah. So you can see, we want to replace 2 by n. Can we do that? Replace 2 by n and make the value larger. That's the intuition. Replace constant 2 by n. Can we make the result value larger? Yes. But we need to put this requirement. When n greater or equal to 2, then we get a larger number by replacing 2 by n. How about that? If you can understand that step, then we have n plus 2 less than or equal to 2n, another constant multiple of n, when n greater or equal to 2. Here, you can see we take C1 equals 2. We take C1 equals 2. All right? Yeah. For n0 equals 0. Yeah. Because here, let me just use for n greater or equal to n0, we have this inequality. Two sides. Lower side estimate, upper side estimate. So that's the definition. That's the whole procedure of the solution, the proof. Yeah. When you write the proof, because here I do the diagram, right? Here I do not write the sentence, line organized well. I draw the diagram. Yeah. But when you write the solution in the standard way, make sure you give me the important information. Yeah. You need to give me what is your value of C2. What is the value of C1? Right? And what is the value of n0? Yeah. Here, for left-hand side, we use n0 equal to 0. For the right-hand side, we use n0 equals 2, but you need to combine them. And we pick the larger one. So then we can make both sides inequality hold when you pick the larger n0. Yeah. All right. All right. Again, repeat last time. When you do the proof, you need to give me C1 constant, C2 constant, n0 constant. But when you give me that, you also need to convince me why the inequality holds. Why the inequality holds. You need to convince me. All right? Then you complete the whole solution. All right, so that's the typical procedure. All right, yeah, so that's the first question. Then, the first one I spent a lot of time because I need to explain the definition. After that, for the remaining questions, I can go a little faster because we do not need to go through the definition again and again. We just do C1, C2, and 0. And the convincing part, the inequality, why the inequality holds, that part. All right? Yeah. All right. Our second question, this time, n cubed belongs to big omega of n squared. Remember, we use big omega. What's the meaning of big omega? This time, we only do the lower bound estimate. We do not do upper bound. Big omega means the lower bound estimate. All right? So that means you need to find a constant c, positive constant c. Okay? C n squared, lower bound for n cubed for, you also need to find a positive, non-negative integer n0 for n greater or equal to n0. Yeah. That's the definition. All right. It's pretty easy, right? Yeah. So let's start our work. So our goal, we want to show n cubed greater or equal to n squared. That should be very easy, right? What is the condition? Under what condition this inequality holds? Right? You can see easily, right? Yeah. All right. Yeah. Can you see when n greater or equal to 0, it holds, right? Yeah. Because n can only take integer, right? Can only take non-negative integers. So we don't need to consider 0.3, for example, right? And must be integers, non-negative integers. So this inequality must hold. Yeah. Then, obviously, c equals 1. That's the positive constant. Okay, so we find the c, we find n0, n0 equals 0. Lower bound, convincing argument, yeah, because it is simple, so you don't need to explain a lot why n cubed greater than n squared, right? Yeah, because everyone can understand easily, right? So you do not need to do a lot of explanation when this inequality is too easy, right? Yeah. All right, so we complete our second question. Yeah. Next, our third question. This time a little harder. Yeah. Show that n plus 2 cubed belongs to big theta of n cubed. Yeah. Big theta again, so upper bound, lower bound. Yeah, 2 bounds. C1, C2, positive constants, and n0. Yeah. All right. Here, you can see n plus 2 parenthesis cube. A little harder, right? Yeah. Here, I like to point one way that many students used before. Yeah. It works, but it is not the best way. Yeah. Usually you need to do a lot of work. So I do not recommend that one. So here, let me point that out here first. Yeah. Because many students do it in this way. When they work on n plus 2 cubed, they expand it. Yeah, they apply the formula a plus b parenthesis cube. There is a formula. So they use that. All right. N cubed plus, yeah, so you may search web and find the formula. 3n squared times 2, so that is 6n squared plus 3n 2 squared, right? So 12n. Last term, 3 cubed, 27. Yeah. Yeah. Then they work on this polynomial. Yeah. Upper bound, lower bound, whatever. Yeah. Although you can make it work in this way, but usually you need to do a lot of work. Why? Look at these terms. These terms relatively more complicated, right? Relatively more complicated. Okay? Yeah. So it is not a good way to work like this. Yeah. So the better way, you do not do the polynomial expansion, do not do it. Yeah. Let us work on the parenthesis part first. Do the estimate on the parenthesis part. Then the last step, we take cube. That will be much easier. All right, so let me show you the better way. All right, so we start from n plus 2 parenthesis cube. We just estimate the parenthesis n plus 2 part. We did it. In our first example, we already did it, right? Yeah. So we know n plus 2 greater than n, so then the whole thing cube greater than n cube, right? Yeah, so that's pretty obvious. Yeah. And we know in that situation, we take n greater or equal to 0. So we have it. Yeah. All right, the other side, we did it. So let us just borrow our thinking from example number 1. Oh, yeah, this case, n2. We have n2 equals 1. Yeah. Next, still use the n plus n to cover n plus 2, but we need to have, yeah, here it equals 2n, right? Yeah. We need to have the condition n greater or equal to 2. Yeah. Then after that, we take the cube operation, n 2n parenthesis cube, so that is a times n cubed. That will be much easier, right? Think about how do you do the estimate on this cubic polynomial. Is it much harder? Comparing with this way, much easier. Yeah, so that's the better way, recommendation. Yeah. All right, so then C1 equals 8, and combine, yeah, because we have two different n0 values, we take the larger one, n0 equals 2. Yeah. After that, we have everything. Okay, C1 value, C2 value, n0 value, and we do the necessary work to explain why the inequality is true. That's all we need to do for the third example. Yeah. All right, so next one. Next one, number 4, show that log function. Log function, yeah. So it will be much harder than the polynomial function, right? Log of n belongs to little o of n. Little o of n. Okay, yeah. All right, so here, when we work on the little o, asymptotic notation, usually we need to do the limit. We need to use the limit to prove it. We need to calculate the limit to prove it. All right, but here, one important property you need to pay attention, and here is a discrete variable, not continuous variable. Why I want to point this out, discrete variable, continuous variable, because we connect to the Lobitas rule. Do you still remember Lobitas rule? Lobitas rule, right? Lobitas rule. Lobitas rule, we need to take derivatives. When we take derivatives, we require the variable must be continuous variable. It cannot be discrete variables. So that's the reason I want to point this out. All right, so let's do the work. It's pretty easy, but you need to be very careful. Yeah. So we consider the ratio of two functions, but this time we replace m by x. Because after this substitution, we assume x continuous variable. This time we make the assumption x continuous variable, so we can take the derivative. All right? Yeah. All right. So while we can take the derivative, all right, yeah, here we use the hidden base a greater than 1. Okay, the hidden base. Yeah. All right. But why we can apply Lobitas rule here? Because it is infinity over infinity indeterminate form. What's the indeterminate form? Yeah, because the value of this form is not determined. It can be anything. It is not determined. So here, this is just a symbol representing the ratio of two functions. The limit of the two functions both go to infinity. So we use infinity over infinity as the form of this type of questions. Yeah. All right. Now, let us take derivative on numerator and the denominator simultaneously. We just apply derivative formulas. All right. For the numerator, by the formula, so I hope you can find it, somewhere from a calculus textbook or from web. Yeah. 1 over natural log of a, that's the constant part, then x, variable part. All right, the bottom, derivative of x, that's 1. We use the power rule, so I hope you know the power rule. What's the power rule? X to r, here, the exponent r is constant. Okay, constant. Yeah. So what constant? A constant. All right. Yeah. Its derivative equals r times x to the r minus 1 power exponent. Yeah. That's the power rule. Okay, that's the power rule. Here r equals 1, so you can see the derivative is 1. The power rule. All right? Yep. So remember to use the power rule. All right? All right. Because this power rule, we will use it again and again. Yeah. R could be, not necessary integers. Not necessary integers. R could be, for example, 1/2 is okay. Okay? R could be √2. It's okay. Right? Yeah. R could be pi. It's okay. 3.14, infinite digits after that. Yeah. That's the power rule. Okay, review a little bit. All right. After that, now can you see the limit? Can you see the limit? All right. Yeah. All right. Sorry. Here I have to erase this part. All right. Yeah. I hope you have a chance to write it down if you need it. Okay. All right. After simplification, limit of ratio 1 over natural log of a times x, when x goes to infinity equals 0. Yeah. When we take the continuous variable, this limit goes to 0, then after we go back to the discrete variable, now we can go back because continuous variable, we consider all the possible values. Now we do not need to consider all the possible values. We only consider discrete values. 1, 2, 3, 4. The ratio, the limit is still the same. Okay? That's by the definition of limit, right? Yeah. So here I do not want to review the definition of the limit, because it is very complicated. Yeah. Here I just say, by the definition of limit, we can switch discrete variable to continuous variable. It is true. Yeah. So we have, yeah, if we replace here, what I mean, we can say from this result, we can say limit of when n goes to infinity, log of n over n equals 0. Yeah, 0 from the continuous version. Continuous, more general, right? We prove a more general case, it is true, then we consider special case of that general case. It should also true. Okay? Yeah? Yeah. The more general case, it covers more cases, right? Now we only look at special case. Still, it must be true. Yeah. So that's the logic. All right. After that, after we find the limit, then we can say, yeah, little o. The conclusion, log of n belongs to little o of n. Okay, so that's example number 4. Yeah. Example number 5, yeah, here. Yeah. So let me see if I can finish that. I need to control my time. Yeah, I just have about 10 minutes left. If I cannot finish, I will cover the remaining part. I will cover the remaining part in part D. Yeah. Part D, I will complete remaining examples. All right. The 5th one, show that n to the d power, this time for convenience, we assume d integer. Okay? Yeah. But later, we will relax that condition because d is not necessarily integer. Non-integer, this result still holds. Yeah. But if we consider non-integer number d, the proof will be more complicated. So we want to avoid that complexity, yeah, make our proof as easy as possible, so we make that assumption. Yeah. Yeah. But after that, later, after we have the solution, we need to adapt our solution to a more general case. It will not too much harder. Just a little more work, we can get it. All right. Here we assume d greater or equal to 1. But actually, later, this condition can be changed. Yeah. All right. But it should be positive. Yeah. Later we make this condition d any positive number, any positive constant. This result should work. Yeah. All right. And a greater than 1. Yeah. All right. So under all the assumptions we make here, we want to use the Lobitas rule to prove it. Yeah. So let us use the Lobitas rule. This example, we need to apply the Lobitas rule several times. Yeah. So for that reason, we make friendly assumptions. All right, so let's look at the work. First, you can see we switch to continuous variable first from n to x. Yeah, from n to x. Yeah. So this time we can apply the Lobitas rule. Why? Yeah, why? Indeterminate form. Remember, it follows the indeterminate form, infinity over infinity. So we need to check it. If you do not check it, some of you may skip this step. Then, if you sometimes in some pretty special situation, if you skip this step, you may apply Lobitas rule in the wrong place. So you get ridiculous result. That's possible. So this check is necessary. After that, then we can take the Lobitas rule, derivatives, numerator, denominator, without any problem. All right, so first, the derivative of the numerator, power rule. D times x to the d minus power rule. The bottom, you need to find the formula. The bottom, you may not be able to memorize this formula, but I hope you can find it somewhere. It equals natural log of a parenthesis times original function a to the x. Okay, then we do simplification. After this step, let us do simplification. We do not need to do simplification, but think about when d minus 1 is a positive integer, it is another infinity over infinity form, indeterminate form. So we can apply Lobitas rule another time, right? Here, let me apply another time. Then d times d minus 1, power rule another time. X to the d minus 2 power, denominator, natural log of a, this time square, because another time you get another constant, natural log of a, so combine the previous one, that square, that number square, and original function a to the x. All right, keep thinking in this way, right? Keep thinking in this way until the ratio is not in determinate form. Then you can stop. Otherwise, you need to keep going. Otherwise, you need to keep doing this repeatedly until you get a non-determinate form. So what is non-determinate form? Let me show you when you get to this one. Okay? When you get to this form. D factorial. Because eventually you will do d times d minus 1 times d minus 2 all the way down to 1. When you reach 1, you get d factorial. Then the variable part, d to the d minus d, right? Because d minus 1, you do minus 1 d times, right? So d minus d as the exponent number. D minus d, the denominator, parenthesis, natural log of a to the dth power, and a to the x. But this time, look at that. The numerator, the variable part equals 1. If equals 1, this ratio is not in determinate form anymore, right? It's not in determinate form. So you have to stop right here. You cannot apply Lobitas rule another time. You cannot. Okay? It will be wrong. So that's the reason I ask you to check if it is in determinate form before you apply the Lobitas rule. Here, after we check it, we cannot apply Lobitas rule. So we have to stop and we need to find the answer. All right, let us do the simplification. We get this one, simplification. After that, when x goes to infinity, the denominator goes to infinity, the whole ratio goes to infinity. So you can see the answer is 0. The answer is 0. Then that means if this answer is 0, that means we can switch to discrete variable n. So we can, because that's the special case, right? From general case to special case. So we have n to the d over x to, a to the n. This limit also 0. All right, yeah. After that, then we can say this little o conclusion. Little conclusion, yeah. All right, so that is our example number 5. Yeah. Here, the remaining time, I think I can only do one more example, last example. Then we have to stop and move the remaining part to part D. Yeah. All right, the last question of this video, question number 6. Show that log base 2 of n belongs to big O of square root of n. Square root of n. All right. Still, we take the limit and switch to continuous variable. All right. And we know here, you also check, it is infinity over infinity indeterminate form. Yeah. So we can apply Lobitas rule. Yeah. Before we apply the Lobitas rule, we write the square root of x, root x as a power function, x to the 1/2 power. So that exponent 1/2 not necessarily integer, right? Yeah. As I mentioned before, when we apply the power rule, the exponent number is not necessarily an integer. So 1/2 is okay. Yeah, we can apply it. All right, let us take derivatives. Numerator, denominator. Numerator by the formula. Yeah, the formula, yeah. 1 over brackets, natural log of 2, parenthesis, constant factor times variable x. All right. Denominator, apply the power rule. Right? Yeah. Exponent number 1/2 times x to the 1/2 minus 1. 1/2 minus 1. That is negative 1/2. Negative 1/2. Okay. Then let us do the simplification. Yeah. After simplification, yeah. 2 numerator over natural log of 2 times x to the 1/2 power. This is not indeterminate form, right? Yeah. The numerator is constant. It's not a determinate form. Yeah. So we should not use Lobitas rule another time, and we can get the limit immediately. It's 0. When x goes to infinity, it is 0. So after that, then we can go back to the n case. N goes to infinity. Log base 2 of n over root n. This limit also equals 0. Then we have the conclusion, little o. You know, this little o statement, we have it. We prove it is true. Okay? All right, so look at, you know, we did 6 examples in this video. Yeah, remaining, we have 3 more. Number 7, number 8, and number 9. So we need probably another, let me see, 15 to 20 minutes. Another 15 to 20 minutes. So I leave that part to part C video. Yeah. All right. Yeah. So let me stop here. Yeah.